This video covers the chain rule. All right, hey calculus students. Today we're talking about the chain rule. So what we've done so far is the general power rule where we have x to the n, some number over x to the n, and we've done basic trig functions that have like sine, cosine, tangent, and so forth. For all of those things, we've had essentially a single x to some power as our the thing that we are deriving. The chain rule involves if we have, for instance, a function raised to a power, and we're going to say, generally speaking, we want n to be greater than 2, because then we can't either multiply it out or likely can't apply some sort of identity. The same thing is going to go for if we have some number over a function to some exponent, or if we have sine, cosine, tangent, and so forth. And later on, we're going to add in e to some function and the ln of some function. All of these things require the chain rule. And so there's this rule that is like if you have more than just an x, you're probably going to need the chain rule. There's no hard and fast method for it, but generally if you have more than just x, it's going to require the chain rule. For example, if we have just f of x equals x squared, doesn't require the chain rule, its derivative is 2x. But if we had something more sophisticated, such as, so we'll have f of x equals, we'll say like 3x plus 1 squared. This requires a chain rule. And so what we learned in class was that the derivative of a composite function, which is what the chain rule derives, is the derivative of a composite function is the derivative of the outermost function times the derivative of the inside function. Notice we did not change the input. The input here was g of x, the input here is g of x, and then we multiply by the derivative of the input. So we're going to call this derivative of outer times the derivative of the inner function. We are going to work practice problems just from the textbook. We're doing page 137 through 140. We'll probably do 7 or 8 examples. The first one is, I'm doing number 7. So number 7 is y equals 4x minus 1 to the third power. So if we look at this, we have two different functions happening. We have a function raised to the third power, and the inside, the input, this g of x is 4x minus 1. The outer function, the f of x, is x cubed. So when we do our derivative, we're going to have y prime equals, the derivative of anything cubed is 3 times that thing squared. And then the chain rule says we multiply by the derivative of the inside. So the derivative of 4x minus 1 is just 4. And then we simplify what we can. So we get 12 times 4x minus 1 squared. So once we've done all of our deriving in one step, we don't need to keep taking derivatives. Even if we ended up with an x here, we wouldn't try to do something like the product rule. It's important to distinguish the chain rule from the product rule and the quotient rule. The chain rule is necessary to generally find derivatives, and the product rule and quotient rule are situational. In the case that we are multiplying, we have to use the product rule to find a derivative. In the case of dividing, we need to use the quotient rule, and the chain rule might be a part of doing either one of those. It doesn't exclude the product or the quotient rule. The second example that we have is number 20, and that is y equals negative 5 over t plus 3 cubed. So this is an example of a problem that does not require the quotient rule because we have a number over a function. So the better step is to rewrite this so that it's -5 times t plus 3 to the -3 power. So we have y equals -5 times t plus 3 to the -3. And this derivative is -3 times the derivative of anything to the -3rd power. We multiply to the front, so we get positive 15 t plus 3 to the -4. And then technically we multiply by the derivative of t plus 3, which is 1. And so this simplifies to just be 15 over t plus 3 to the 4th power. So notice we move the negative exponent back down to the bottom. The derivative of 1t is just 1. Again, no quotient rule. The next example that we will work is one with the trig function, where we have, so this is number 48. We have, we'll make it f of x equals the secant of x squared. Only the x is squared. So when we do this derivative, we're going to have f prime of x equals, so the derivative of secant is secant of the angle times the tangent of the angle. And so the derivative of secant tangent. And then we also must multiply by the derivative of x squared, which is 2x. So this simplifies to be 2x secant x squared tangent x squared. Over here to the right, we're going to work an almost parallel example where we'll make this f of x equals, and in parentheses, we're going to do secant x squared. And so when we do this derivative, the derivative of anything squared is 2 times that anything to the 1st power. And then the chain rule says that we multiply by the derivative of the thing that was raised to the power. So that's going to give us secant x times tangent x, because that's the derivative of this. So that gives us 2 secant squared x tangent x is the final answer. Again, note the difference between these two. Here, the x is squared. We ended up with 1 secant and 1 tangent. Here, the secant was squared. We ended up with the secant that we started with multiplied by its derivative. Our next example is number 50. And for number 50, we have y equals the cosine of 1 minus 2x squared. Again, the input or the angle is what is squared, not the cosine. So our derivative is, the derivative of cosine is negative sine. We never change our angle. So negative sine 1 minus 2x squared, and then multiply it by the derivative of 1 minus 2x squared, which we'll put in a bracket. So we multiply the 2 to the front, we get 2 times 1 minus 2x to the 1st power, and then we multiply by the derivative of 1 minus 2x, which is -2, and we close that out. So going back through this, the derivative of cosine is negative sine. The derivative of 1 minus 2x squared is 2 times 1 minus 2x, and then the derivative of 1 minus 2x is -2. So we start taking derivatives from the outside and keep working our way to the inside until we've derived everything, never changing the input along the way. So when we fully simplify this, we get 2 times -2 is -4, times negative sign is +4. So, you know what? We'll put the algebraic part first. So this will be 4 times 1 minus 2x times the sine of 1 minus 2x quantity squared as a final answer. So that was example 4. That was our 4th example. For our 5th example, we're going to start combining the product and the quotient rule. So we have 23. We're doing f of x equals x squared times x minus 2 to the fourth. All right, we're going to change the x minus 2 to be something slightly more complicated. Let's make it x cubed minus 4, and we'll make that to the third power. So I changed number 23 slightly so that we can see the chain rule action. So we have f of x equals x squared times x cubed minus 4 cubed. The multiplication between one function and another function indicates that we have to do the product rule. So remember, the product rule is the first function, which would be x squared, times the derivative of the second function. To do the derivative of x cubed minus 4 cubed, we just have to do the chain rule. So this is going to be times, and then the derivative of x cubed minus 4 cubed is 3 times x cubed minus 4 squared, because the derivative of anything cubed is 3 times that something squared. And then we also multiply by the derivative of the inside, which is 3x squared. So all of this is just the derivative of x cubed minus 4 cubed, which required the chain rule. And so then we have plus x cubed minus 4 cubed multiplied by the derivative of x squared, which is 2x. So if we simplify this, we get x squared times 3x squared times 3. That's going to be 9x to the fourth times x cubed minus 4 squared plus 2x times x cubed minus 4. Oh, make that a better parenthesis. All right, so for me, this is a fine final answer, but you may be asked, I left out the cube, I'm sorry. So this was cubed, that should be cubed. So this is a fine answer, but you may come across answers that are fully simplified by taking out a greatest common factor. And in that case, they both have an x and an 2x cubed minus 4 is a power of 2 in common. So if we factor this, we could have x times x cubed minus 4 squared, and then that would be times 9x plus 2 times x cubed minus 4. We could distribute the 2, but we're going to say that's overkill. So this is a proper final answer, and this is an unsimplified final answer. Again, notice that we had to do the product rule, which required that we do the chain rule. Sometimes we do the product rule without having to do the chain rule, but anytime we have a function raised to a power, the chain rule is going to be necessary. So that was example 5. Example 6, we have a case of where we're going to have to do the quotient rule, and we're going to make this. So we'll make it g of x equals, I'm sorry, you can see that now. So g of x equals 3x squared minus 2 over 2x plus 3. All of this is raised to the third power. Fix that. So to do this, we have the derivative of something cubed. So we're going to have g prime of x is equal to, again, the derivative of anything cubed. You know what? Let's make it a 5 instead. We'll just make it a 5 so it's different. The derivative of anything to the fifth power is going to be 5 times that something. So 5 times this something to the fourth power. And then we also have to multiply by the derivative of the inside. And doing the derivative of the inside requires that we do the quotient rule. So we're going to have the low function times the derivative of the top minus the top function multiplied by the derivative of the low function all over the low function squared. So as a final answer, we're going to keep the 5 times 3x squared minus 2 over 2x plus 3 to the fourth and simplify some stuff. So when we multiply it, let's create a fraction. 6x times 2x is 12x squared plus 18x. and we're distributing -2, so minus 6x squared plus 4 over 2x plus 3 squared. Now, if we keep going, all right, let's pretend that we just keep this in the problem. This drops down here. If we keep going, 12x squared minus 6x squared is 6x squared plus 18x plus 4 over 2x plus 3 squared. Now, for me, this is sufficient, and we can factor out a 2, so we finally get 10 times 3x squared minus 2 over 2x plus 3 to the 4th times, we'll need the open parentheses, times, if we divide 2 out of this, we would get 3x squared plus 9x plus 2 over 2x plus 3 squared. So again, we factored out a 2 and multiplied it by this 5. We took out the common factor of 2 here and multiplied it by that 5 that we dropped down here. We just didn't feel like writing it. So again, we did the chain rule, and part of the chain rule required that we do the quotient rule to find the derivative of the inside. So that's our 6th example. And so then example 7 is, what happens if we have a trig function inside of another trig function? So imagine we have y equals sine of tangent x squared. So again, I changed number 65 slightly. Instead of having tangent 2x, I did tangent x squared. The derivative is going to be, the derivative of sine is cosine, never change the input. So cosine tangent x squared, and then we multiply by the derivative of tangent x squared, which is going to be secant squared x squared, never change the angle, and then we multiply by the derivative of x squared, which is 2x. So our final answer is 2x cosine tangent x squared times secant squared x squared. Okay, so our final example is going to be one of these more open questions where you're given some information and you have to determine if something exists. Here we're trying to find f prime of 5 if possible. So we're given that g of 5 is -3. The derivative of g at 5 is 6. H of 5 equals 3, and h prime of 5 is -2. So for part A, we know that the derivative is g prime of x times h of x plus g of x times h prime of x. And so, yes, we can find f prime of 5, because it's g prime of 5, which is 6. We'll put that in parentheses. 6 times h of 5 is 3 plus g of 5 is -3, and h prime of 5 is -2. So that's 18 plus 6, which is 24. So yes, this one is possible. So for B, we have f of x equals, f prime of x is, so the chain rule is derivative of the outside, which is g prime of x, multiplied by the derivative of the inside, which is h prime of x. So f prime of 5 is equal to g prime of h of 5 times h prime of 5, which equals g prime of h of 5 is 3, so g prime of 3 times h prime of 5 is -2. And so we don't know g prime of 3. We were only given this information. So we're going to put can't go further, or can't go farther with, well, was it farther? Let's go further without g prime of 3. So the answer here is no, because we don't have enough information. For letter C, we have f prime of x is, all right, so let's use some shorthand. We have the low function times the derivative of the top minus the top function times the derivative of the bottom over the bottom function squared. F prime of 5 is going to equal, so h of 5 is 3, g prime of 5 is 6, g of 5 is -3, and g prime of 5 is, I'm sorry, so g of 5 was -3, and h prime of 5 is -2, and all of that is going to be over h of 5 squared, which is going to be 3 squared. So the answer to this one is yes, it's possible, because we have numbers in every spot. That's going to be 18 minus 6, which is 12 divided by 9. So 12/9 or 4/3. And so then the last one we're going to do for this video is the derivative of f would be 3 quantity g of x squared times g prime of x, which would make f prime of 5 equal to 3 times g of 5 squared times g prime of 5. So again, because we know g of 5 is -3, -3 squared is 9 times 3 is 27. So 27 times g prime of 5, which is 6, is 4,262, I believe, quickly. 6 times 20 is 120 plus 42 is 162. Yeah, 162. All right, so that concludes our video over the chain rule. The chain rule is a multifaceted approach to finding derivatives. Anytime we have a more complicated function, we need the chain rule. It doesn't just exist for polynomials. It exists for trig functions, exponential functions, logarithms, algebraic functions, square roots, inverse trig functions, and all that stuff. So we're going to use that property as we continue to move. And let's put a star by this, and in parentheses write use substitution. That's going to come up when we do integrals, and the chain rule is going to be important to that. So the takeaway from this is that given a composite function, the derivative is equal to the derivative of the outermost composite function, and then we multiply by the derivative of the next inner composite, the inner function, and we keep multiplying until we've gotten to the end. If you have questions, please see me in class, possibly rewatch the video. I would encourage you to work examples from the textbook to see if you understand. You can bring those problems to me and we will discuss them. Thanks.